Just as we did when we were given a vector parallel to a line and a point on the line, we came up with a set of parametric equations that describes the line. We want to do something similar with a plane in space. And what we're going to need to describe the plane in space is we need one point on the plane, and we need a vector that makes a perpendicular with the plane. So, in other words, if you're on the plane, it will stand straight up. So we need a vector that's perpendicular with the plane. We're going to call this the normal vector, and I'm going to denote it A, B, and C like this. And then I'll just say, okay, x naught, y naught, z naught is a point on the plane. Kind of draw you a picture. Here is the point. So here's the plane, kind of a representation of the plane. Here's the normal vector. Now, we're going to proceed this way. I'm going to say that there's just another point on the plane I'll call Q. And I'm going to identify Q, and what we're going to have is we're going to have it make a vector with P. So P is the initial point, Q is the terminal point. And what I'll do, I'll say this. I'll say that PQ, let me just write it in this form. We've got x minus x naught, y minus y naught, and z minus z naught. That's my PQ. We know this, that since this normal vector makes a 90 degree angle with the plane, then it also is orthogonal to the vector PQ. In other words, PQ, if you dot it with that normal vector, what you're going to get is 0. We know this because that's a property of dot products. If you dot orthogonal vectors, you get 0. So let's see what this looks like now. Let's go ahead and actually do the work here. So if I dot this, if I have x minus x naught, y minus y naught, z minus z naught, and I dot that with A, B, and C, here's what I get. I get A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught. And we know that that dot product equals 0. Now, I don't want to leave it like this. I want to go ahead and liberate out the A, B, and C, or the x, y, and z. So I get this. I get ax plus by plus cz. And notice you can easily identify the components of the normal vector, A, B, and C. And then let me put the rest of it all together. I've got plus, now let's do the rest of it, negative ax naught minus b y naught minus c z naught equals 0. And I'll call this part right here just a constant. A, B, and C are scalars. X naught, y naught, z naught are scalars. So this is just a constant. So I'll say this is ax plus by plus cz is equal to, oh, well, don't forget the plus d. Plus d is equal to 0. So that's our equation for the plane that contains x naught, y naught, z naught, and is normal to the vector a, b, and z. Or, well, the normal vector with components a, b, and c. So let's look at a particular example here. Let's suppose that my normal vector is negative 2, 3, and 5. And we want the equation for the plane such that this is the normal vector, and it contains this point. Let's just make up a point here, 1, 7, and negative 3. So let's see what this looks like. So we're going to do this. We're going to take the x component of the normal vector, x minus 1. See? Okay. So there's the 1 right there. And here's the negative 2. Now we take the 3 and do y minus 7. And then finally, the 5z plus 3 equals 0. So we can quickly identify the point. The point is 1, 7, and -3, and the vector is -2, 3, and 5. Those are the components of the vector. Now let's go ahead and finish this off. We've got -2x plus 3y plus 5z. Now let's get the rest of it. Plus 2 minus 21 plus 15. Okay, and there's what we have so far. Now let's go ahead and go through here. -2x plus 3y plus 5z. Now let's see here. This is going to be 15. There's 17 plus 21. So there's 17, well, not 17 plus 21, 17 minus 21. And this equals 0. So finishing this off, -2x plus 3y plus 5z minus 4 equals 0. And there's the equation for the plane. And you can very quickly see the normal vector, -2, 3, and 5. So that's the way we're going to write the equation for a plane.